Hi, an example for single proportion tests. So suppose that the null hypothesis is equal to p is equal to 0.5, and our sample proportion is 105 over 200, that is 0.525. That we want to see if this p hat is plausible under null hypothesis. And the z statistic discussed in the previous video is the p hat minus p naught. So that is 0.525 minus 0.5 divided by the standard error of p hat. That is the square root of p naught times 1 minus p naught divided by sample size. And that is the 0.707. And you know that the 0.707 is a typical value of standard normal, the random variable. So standard normal random variable, the 95% of observations are covered between negative 1.96 and positive 1.96. So 0.707 is around here. So this is the typical value of the distribution. So we do not reject the null hypothesis at 5% level. So assumption that the true proportion of male babies is 50% may be a plausible assumption. Yeah, so this is the R code for that one and the prop.test function. So we put the numerator of our sample as the first argument and the denominator as the second argument, and our hypothetical probability is the third argument. Then it can test the hypothesis 105 out of 200 with null probability 0.5. Then x squared value is reported. So this is basically the z square. So the square of standard normal random variable is called chi-square distribution with df1. So that's why that we say the R reports this as the chi-squared and the df1. So that means we always do two-sided test here. And the p-value becomes 0.5245. So the p-value is larger than 0.05. So we do not reject null hypothesis, not reject H naught of p is equal to 0.5. So p is equal to 0.5. There may be the possible value of p. And what's the typical possible value of p? So we have the concept of the 95% confidence interval. So that means if true p is within this range, our p hat is plausible. And actually the range of the true p is between 0.453 and the 0.596. So with this range, the p hat of 0.525 is very plausible. So this is the 95% confidence interval. Yeah, and okay, so I said that the 0.405 is the z square, but actually it's not exact. So if we got the z value of the 0.707 or 0.706 from the hand calculation, and if we square this quantity, that becomes 0.498. That is different from 0.4085. So this comes from so-called the continuity correction. So we approximate, excuse me, we approximate the discrete distribution by the standard normal distribution. So originally we have the, so sample proportion, but if we think about the 200 times sample proportion, that is the maybe, so sample portion itself. This ranges from 0 to 1, but the increment is 200, 1 over 200. So possible values, for example, 100 over 200 is possible, but the next possible value is 101 over 200. So distribution is like this. So it's discrete. And discrete distribution was approximated by continuous curve, normal curve, so like this. So we have some discrepancy. So if we take, for example, the 102 over 200 here, then the p-value should be area of here, and possibly the other way around, so the area of here also. But we do normal approximation, so actual probability we calculated is from here to here, and we along this curve itself. So this yellow area and orange areas are different. So on the left-hand side, it's the same. So we need some continuity correction, especially that this part is different, so that we have to correct it. And the R did continuity correction. So actually, the R calculation of z square of the 0.405 is more accurate. Yeah, so in general, if your result is slightly different from R, probably the R did some adjustment for a better approximation or a more exact solution, so that you can rely on it. Yeah. And another way to test the sample proportion in R is using the binomial.test function. So binomial.test function, this doesn't use any approximation. So if we have the 200 observations and we observe 105 over 200, R basically calculates the probability of the p hat is equal to 0 over 200, 1 over 200, 2 over 200, up to 100 over 200, 101 over 200, and up to 200 over 200. So R calculate all probability, and that we make the rejection region. So it's more exact test. But still, the p-value is almost the same. So that means the sample code 2 gives, the second code gives more accurate results than the first one, because we don't use approximation. But anyway, the two results are very close. So if the sample size is small, maybe the discrepancy is large, but the sample size is large, almost no change. So they use the first test. It's much quicker, and result is anyway almost the same. Yeah, so we have discussed a confidence interval for the test. So both the first code and the second code include the confidence interval, and how to calculate confidence interval. So that is the here. So the formula is the p hat plus minus the z sub 1 minus alpha over 2. So this is the quantile point. And the area below that point is 1 minus alpha over 2. So this is z sub 1 minus alpha over 2. So this value times the standard error of p hat. So that is calculated as this one. So p hat plus minus the quantile point times this standard error. That makes the confidence interval. So this is basically the interval. So say this interval is AB. Then the probability of the P is between A and B is equal to 95%. So remember that A and B are random variables. So this depends on P hat. So this is random variable, and these are random variable. So we can think about probability that P is between A and B. So this is the formula for confidence interval. So sometimes that we use instead of this standard error, that we use the standard error of p hat as square root of 0.5 square over n. So because this is the largest possible value of standard error of p hat. So think about this equation, this quantity, the p times 1 minus p. So if we think about this function, the p times 1 minus p, so this is maximized at p is equal to 1/2. So P ranges from 0 to 1. And this is the parabola. And 1/2 and 1. So the graph of the y is equal to p times 1 minus p is this. So this is the largest possible value. So this is actually the more conservative. So we are on the safe side. So our calculated confidence interval has at least 95% confidence. Yeah, or we can say that the 50% is the most, variable. P is equal to 0.5 that gives the most uncertainty, or most variability. So that's why the 0.5, using 0.5 is on the safe side. And from the previous example, how to calculate the 99%, for example, the confidence interval. So that is the p hat plus minus the z sub 0.995 times that is the square root of p hat times 1 minus p hat. Okay, so this is p hat, this is 1 minus p hat divided by sample size and the stake square root. And this value is actually 2.576. If you use R, then you can use the Q norm function and the 99.5%, and you can this. Then we can calculate the square root part, so this one. So we can get the 0.434 to 0.616. So it's a little wider than the previous one, but the one are reported, but this is because of the continuity correction. So just approximation error.